Thank you, Carsten. So this is about our paper, Weighted Rewriting. I'm Martin. It's joint work with Akihisa Yamada. And this paper is about abstract reduction systems. For those who don't know abstract reduction system, in its maybe most simple form, an abstract reduction system is just a set of objects equipped with a binary relation, the reduction relation. And this simple setting is already quite useful to reason about general properties of reduction, such as termination, confluence, unique normal forms, and so on and so on. Okay? In particular, I think it's not an exaggeration to say that, well, this theory around abstract reduction system has been developed almost since the birth of the computer science discipline. And it underlies nowadays many fields of computer science, think about functional or declarative programming, if you think about ITP, theorem proving, and so on and so on. Okay. However, as nice as abstract reduction systems are, they do not capture certain quantitative aspects of computation very well. In particular, two of my research interests, the first one is kind of complexity or more generally resource analysis. And another research interest of mine is the analysis of probabilistic programs. Well, if you look at probabilistic programs, for instance, this is a formalism that is inherently quantitative because computation always happens with an associated probability. Okay, so the main purpose of our paper is to at least provide a first step to develop a theory in line with the theory of abstract reduction systems, but that has a much more quantitative flavor so that we can, for instance, more nicely reason about complexity properties or quantitative models of computation such as probabilistic programs. So this is the outline of my talk. Our, well, step towards such a theory is the notion of weighted abstract reduction systems. So weights are our notion of incorporating quantities into this model of computation. I will then try to convey that this is a useful model by presenting some instances. And then the idea is to kind of build a theory around this model, like we have for abstract reduction systems. And of course, such a theory should eventually be huge. And here this paper is just the first step where we focus on one particular essential property, namely termination, or more precisely, a quantitative version of termination, which we call boundedness. So I will introduce these new quantitative properties, and then I will also talk a bit about proof methods, namely embeddings and ranking functions for reasoning about boundedness. So the first step with this goal in mind is you can ask yourself, how do you incorporate quantities into an abstract reduction system? Well, we were not the first one to ask this question. One idea is, for instance, to equip your objects with quantities W. Okay, but if you think this way, in particular, if you think about the application domains that I was thinking about before, it's maybe not such a useful formalism. One that is much more useful. Why? Because these properties these quantitative properties I will be talking about are not so much properties of the objects that you're rewriting, but more inherent to the computation. So another way is to, instead of endowing objects with quantities, you can turn your reduction relation into a more quantitative object, like a function which associates to your step a quantity. Okay? So you turn a relation, which you can see as a Boolean function over pairs, you generalize it from Booleans to quantities W. And this has been done, for instance, by Gavazzo and Florio in their 2023 Poppel paper. Now then, to develop a rewriting theory around this one, however, you need quite some structure around your weights W. Here they choose quantals, which essentially is a combination of a monoid and of a lattice structure in order to, well, the monoidal structure is used to combine weights of your reduction steps so that you can do several steps in a row. But then at the end of the day, you want to have a function, so you want to resolve kind of non-determinism. You use the lattice structure to combine parallel steps informally. So this is kind of nice, but it puts a lot of constraints on your weight. A more simpler and more general constraint is to just endow your reduction steps or to let your reduction steps directly carry a weight. And this is the approach that we have chosen. And if you look carefully at the literature, you can actually find many instances, in particular, maybe in a related field on automata theory. There are weighted automata where now the transition relation carries a weight. And these have been employed, for instance, for cost analysis, natural language processing, and so on and so on. You find it also in the rewrite system. And also, since I've been starting to work on the analysis and also on semantics of probabilistic programs, this is more or less the underlying theme, how me or myself, together with colleagues like Akihisa, have modeled probabilistic reduction. And so this kind of gives you a motivation for our central definition, namely the definition of a weighted abstract reduction system. It's like an abstract reduction system, but now each step, each production rule carries a weight. Okay, so it's a ternary relation. W is the weight of the step, which, for instance, you can understand as its cost or another quantitative measure of the step. A and B and the two A's are the source and the target of your reduction. With a slightly nicer notation, A, R, W in brackets B means that A goes to B with weight W. Okay? So this ternary relation morally defines a single step, but then when you want to build a rewriting theory, you want to, of course, compose steps. And for that, you need a way, for instance, to compose weights when you do two iterative steps. And to that end, we suppose that we assume our monoid, our weights have a monoidal structure, where the structure now defines how we can compose weights when we do multiple steps in a row. So maybe put in a bit of another, from a different perspective, we can, using a monoid, we can define this notion of weighted order, which is a reflexive and transitive order, where reflexivity, the weight, is the zero of the monoid, and the transitivity is given, well, as you expect for a transitive relation, but now you use the monoidal binary operation to combine two weights of two successive steps. And so now with this definition in place, we can say that the reduction order induced by such a weighted ARS is just the least extension of this weighted ARS that is a weighted order, so transitive and reflexive. This gives us the basic blocks or the basic ingredients to do now rewriting. So in particular, we have now a notion of transitive reflexive closure, transitive closure, and also a notion of normal forms. So to make this a bit more precise, what are instances? Maybe the most trivial one is just the embedding of ordinary ARSs by associating a weight 1 to each step. And then you will see that actually all these notions quite nicely work out. So in a way, this gives you a good feeling because it tells you that this way our notion of weighted ARS and the notions that we just have defined are kind of, well, give you a conservative extension of ordinary AISs. A bit more interesting example is that of weighted first-order term rewrite system. So a first-order term rewrite system is usually just a rule on terms, so your objects are terms. Rules you should just understand as equations that you can apply in a directed way from left to right. So here is, for instance, an example of a term rewrite system that recursively defines addition on natural numbers. And then here you have associativity rule, also extra. Now you can say, okay, how do we weight a term rewrite system? We just weight its rule. This gives rise to the notion of weighted rewriting, of a weighted rewrite system, term rewrite system. How do you perform reduction? Well, in classical term rewrite systems, as I mentioned before, it's just you rewrite terms by applying rules from left to right. Okay, put this a bit more formally. Usually one defines a rewrite relation as the least extension of the rewrite system that is closed under context, so you can apply a rule deep inside a term, and substitutions, so you can rewrite instances of the rule. And the same thing carries over to weighted rewrite systems. Okay, you can define a notion of weighted rewrite relation, maybe it's in its most simple form, just by taking the closure under context of substitutions of the weighted rewrite system. To make this a bit more concrete, here with these above two rewrite rules, here you have the term Sx plus 0 rewrites with, at the root position, with the second rule, with a weight of 2 to that term. Now here, because of closure under context, you can rewrite an argument of S, and so on, and you reach to some normal form. So overall, you can rewrite Sx plus 0 to S of x with a weight of 3. A more interesting example is that of probabilistic abstract reduction systems, a notion that was introduced by Bonnet and Garnier. I don't want to go in, too much into detail. The difference to classical AISs is now that your reduct is chosen from a probability distribution. So here you have an example. It describes a random walk on the natural numbers. You walk from n to n minus 1 with probability 1/2, or to n plus 1, again with probability 1/2. You stop when you have reached 0 because there is no rule. Now, if you want to model reductions, this becomes a stochastic process, or what we realized in 2018, you can also give a rewriting semantics using an abstract reduction system, where now the objects that you're writing are multi-distributions, which are kind of a generalization of distributions. Okay? And then you can define the probabilistic rewrite relation given by such a probabilistic AIS as the least extension of this weighted AIS that is closed under convex sums. So if you can write a distribution or multi-distribution mu I or multi-distributions mu I to nu I, then also you can rewrite the convex combination. This sounds, well, maybe a bit contrived, or at least not very intuitive, but it gives you very nice induction principles to reason about probabilistic reduction steps. If you look at an example, what it really just says, this definition is that, well, you kind of rewrite sets where your objects are annotated by probabilities, and then you can apply the rules of this reduction system from left to 1, taking the probabilities into account. From W0 in one step, you reach W1 in one step by the first rule, you reach W0 with probability 1/2, or W2 with probability 1/2. Now this is kind of a normal form. This you can further reduce. Okay, so with probability 1/2, 1/2 times 1/2 is probability 1/4. You go from 2 to 1 or to 3, and so on and so on. Okay. Now, you can also generalize this a bit from multi-distributions to arbitrary objects. If you have, well, if your objects A are kind of convex spaces or barycentric algebras, maybe I should not spend too much words on this one, but the idea is that in this general setting, you can, for instance, model probabilistic AISs that we just have seen, but you can model more. For instance, here is an example of a chemical reaction, and here this is an interesting reduction system that we will see later. The objects are real numbers, and the x is bigger than y with weight w, if x is greater or equal than y plus w. Then again, using as this convex operation just the usual sum or usual weighted sum that you have on reals, you see that this one is convex closed. I should hurry a bit up. So I hope I gave you a bit of an intuition about weighted AISs. So now you can ask yourself, what are the properties that we are interested in? And of course, you can kind of, on the one hand, lift the qualitative properties that you have from abstract reduction systems, like weak normalization on a set S means that every element A in the set can be reduced to a normal form, and in contrast, strong normalization on a set S means that all your elements in the set, whenever you rewrite, your rewriting sequence will be terminating. So obviously, strong normalization induces weak normalization, but then you can also ask quantitative properties. Okay, now we have these weights. You say that the weight of the reduction is just the sum of the weights of all your individual steps. If you have weights that are partially ordered, you can ask yourself whether the total weight of a reduction is bounded. Okay, so this gives you a bit more like a complexity flavor. And then here you can define this notion, what we call weakly bounded, means simply that all reduction sequences are bounded. In contrast, there is a slightly stronger notion that we call strongly bounded. It means that for every element A, if you perform a reduction, then you have a global bound for A that binds the weight of the reduction. Okay? And again, strongly bounded is a stronger property than weakly boundedness. Okay? And so here you have this hierarchy now of termination, qualitative and quantitative properties. You can ask yourself, how maybe we missed some relation, but actually this is complete. So weak normalization does not imply strong normalization. If you know that you have one terminating reduction, it doesn't mean that all reduction sequences are terminating. Weak boundedness, so you have an upper bound on your weights. In this example, well, you approach an upper bound 2. Okay, so this AIS is weakly bounded, but it does not have a terminating reduction sequence. Okay, so weakly bounded does not imply normalization and also not strong normalization. So this is what we call a Zeno sequence. However, if you ask yourself, well, if your AIS does not admit a Zeno sequence, then actually strong normalization and weak boundedness collapse. Now, the last question is about the relationship between boundedness, weak boundedness and strong boundedness. So weak boundedness requires that whenever you do a reduction, the weights of the reduction is bounded. But this does not imply that you can attribute to each object a global bound. And in particular, the reason is here each reduction is bounded, but to that note you cannot associate the global bound. And here this is a bit more of a tricky example. So here it's clear the reason for that one is because this system is not finitely branching. Okay? However, if your system is finitely branching, also in this a bit more stronger sense that you see here, then strong normalization implies strong boundedness. So why is this kind of interesting? It's interesting because all these different settings correspond to different classes of abstract reductor systems. In particular here, to the right, you have the setting of the kind of abstract reductor systems that you get from probabilistic programs. Here is the setting of weighted term rewrite systems and so on. Okay. So this brings me to the final part of your talk. Now that we have established this new kind of quantitative termination properties, in particular this notion of boundedness, how can you prove it? And so there are kind of quantitative properties of termination, so it makes sense to go back and to look at termination methods for ARSs and whether you can use them or extend them in such a way that you can prove boundedness. And here this is a very old result by folklore. I did not find a reference anymore for it. It states that the finitely branching ARS is terminating if and only if you can embed the ARS into the order or the natural order or natural numbers. Okay, so what does this embedding mean? Here, this short form, it just means that whenever you have a mapping, imagine it like a ranking function, eta from A to X, such that whenever you do a step from A to B, eta maps that to a step from eta A to eta B in your order. Okay? So it gives you a characterization of strong normalization through this kind of ranking functions. And the proof is very simple soundness. Whenever you have an infinite reductor, you would have an infinite descent with respect to the order of natural numbers. And clearly this gives you a contradiction, so such an infinite reductor cannot exist. For completeness, for the other direction, if you have a finitely branching ARS which is strongly normalizing, you can define the derivation height of an object A simply as the maximal number of steps that you can do. And you will see that this derivation height gives you a corresponding or a good embedding. Okay, so this eta you can understand what people from programming verification call kind of a ranking function. And if you look into it, you realize that embeddings can prove boundedness actually. Okay. So to make this a bit more formal, we introduce this notion of potential of a weighted ARS. It's just the maximal, or it's a function that assigns to A the set of weights that it can produce through reduction. And then you can define this small potential function as the supremum of all the potentials an object admits. Okay? So this potential is usually a partial function, but in the case where we lift ARSs, the potential just corresponds to the derivation height function that we have seen in the previous slide. If you think about probabilistic ARSs, this potential function, so the maximal weight that an object can produce by reduction, just corresponds to the expected derivation height, the average derivation height admitted by the rewrite system. And this potential set gives you kind of a characterization of strong boundedness. A system is strong bounded on a set of starting objects S, if and only if you can find a bound to all the potentials. It's kind of a trivial result. But the point is, you can now see proving strong boundedness that's providing an upper bound on the potentials. Okay? And now you can just take this notion of monotone embedding that I have shown you before and lift it in the obvious way to probabilistic ARSs, where you say now eta is an embedding of one weighted ARS into a weighted order. If whenever you do a step from A to B with weight W, you you have a W decrease in the order through the embeddings. And then you can prove that, in particular, whenever you have an embedding, then strong boundedness of your, well, purple order implies strong boundedness of your original abstract weighted abstract reduction system. Okay, so this gives you the question now, how do I get a strongly bounded order? And here we can look into, well, you have seen this system already. So for this, maybe I show it here. Well, so I don't know if you remember this system. So you have a set of weights W, and you can define a weighted order given for a particular weight by saying X is greater than W with weight W precisely when X is greater or equal than W plus Y. So to each weight monoid that is partially ordered, you can associate such a set. Now, if you think about it, when you have an embedding into this order, this just means that whenever you do a step, then eta of A binds the weight and eta of B. So the rank of A binds the weight plus eta of B. Then you can realize that the potential of this pink order is just the identity function. And if you put all of these steps together, you see that if you have an embedding into this order, then the potential of A, so the maximal weight that you can do, is bounded by the rank that you assign to A. Okay? And our theorem says that, again, this gives you a sound and complete method for proving strong boundedness. Maybe I skipped this one. So now if you go to concrete settings, you can ask yourself, how do I define such an order on terms, for instance? And here we can use this notion of monotone term algebras. Well, a term algebra is just a way to interpret terms into a carrier set A. So this gives rise to an interpretation of terms. And then we can define an order of terms based on an order of the carrier by first interpreting left and right hand sides. Okay? So maybe an example tells you more than different words. Here I choose as order the order on natural numberings. I interpret my terms as natural numbers in the way just that I given the example here. And then what you do is you interpret left and right hand sides, and you check that for each rule in your example, you have a decrease in the corresponding order. And if you do this one, our result again states that the reduction system induced by a weighted term rewrite system is strongly bounded if and only if you can find a term algebra so that all your interpretation functions are monotone. And you can carry also this idea over to barycentric AISs and get the notion of, or a method for proving strong boundedness, for instance, for probabilistic systems. Okay, so in order to leave time for maybe one or two questions, let's conclude. So our paper describes this notion of weighted abstract reduction systems. I've shown you some instances. I've shown you at least one proof method for proving strong boundedness. It instantiates nicely also to the setting of term rewrite systems or weighted term rewrite systems and, for instance, barycentric systems such as probabilistic systems. Future work, there's a lot of future work left. We have looked into termination, but there are other interesting properties we would like to investigate. We have particular applications in mind, and like René asked me before, also formalization in a theorem prover. Thank you.